Have you thought about the significance of this? You know about this well, right? This means work done by a closed system. And actually, this means work done by an open system. So, today's topic is, what is the difference between this and this? You know, this is a conservation law of energy for a closed system. Here is the closed system, and if you give some energy, it will be used for the increase of internal energy and the work that the system produced. An interesting thing about this law is that these are process functions, but this is a state function. I mean, these depend on the path taken to reach one state from another. However, this doesn't depend on the path taken. It's interesting, right? Okay, let's go back to the main topic. This work can be calculated this way in reversible process. I will talk about reversible process after talking about this integral. How much has this system produced? This small part exerts this force, and let's say the displacement of this part is dx. So the work done by this small part is P times ds times dx. But ds times dx is equal to dv. Therefore, dw is equal to P times dv. And that's why this integral means the work done by a closed system. Okay, next topic is reversible process. Reversible process is a process that can be returned to its original state without making any difference to the world. Don't be worried. You don't have to understand this for now, but the conditions that satisfy reversible process is important now. The first condition is that the transition is done quasi-statically. It means the transition is done while keeping equilibrium thermostatically and mechanically. The second condition is that the transition is done without friction. What do these mean? If you pull a piston strongly, the right side pressure PR becomes less than the left side pressure PL. Therefore, the actual work that the piston produced is less than this integral. P means the average pressure in the cylinder. What I'd like to say is that the actual work cannot exceed the work done in reversible process. In other words, the cylinder can produce work most in reversible process. This can be applied to the situation where friction exists. Even though the inside pressure and the outside pressure are in equilibrium, as the piston needs a force against the friction, this theory holds up. I mean, the cylinder can produce work most under the condition where friction doesn't exist. Why do we think about reversible process, even though this process doesn't exist in the world? It's because we sometimes would like to know the most work a closed system can produce. What is an example for an open system? This is the example. You can easily understand what P1 is and P2 is. But what do these mean? V1 is the volume that enters into this open system per unit time, and V2 is the volume that comes out of this open system per unit time. Now, you may be thinking that V1 is equal to V2, but actually, it's not true, because the fluid is compressible. Okay? And this system works in reversible process, which means that this fluid with pressure P1 rotates the impeller while keeping equilibrium without friction. Eventually, the fluid transforms this fluid with pressure P2, and then this fluid is discharged. Okay? Let's try applying the conservation law of energy per unit time to this system. Firstly, this fluid enters into the system per unit time, so we can say this energy enters into the system per unit time. I am sure that you can easily understand that this is energy to enter the system. But why can we say this is also energy to enter the system? Let's think about it this way. This system receives this fluid per unit time. That is to say, this system receives this energy per unit time. As P1 is constant, this integral is equal to this. Therefore, we can say this is also energy to enter the system. Okay? In addition to these energies, this energy is added to the system per unit time. Normally, the system loses this energy, but let me define the direction like this. The fluid enters into the system like this, and this fluid works by rotating the impeller, and then the fluid transforms this way, and after this, the fluid discharged, which means that the system discharges this energy and this energy. Now we get the conservation law of energy for this open system. If we use the idea of enthalpy, the conservation law can be described like this. I just substituted enthalpy into the conservation law. Okay? I will take a note of it. Next, I'm going to describe a conservation law of energy for a closed system. I was talking about this device until a while ago, but I'm going to talk about this closed system. This is a closed system, so the system will be deformed like this in a few seconds. In order to make it easier to express the conservation law for this closed system, I will express the conservation law under the situation where the shape changes in a very short time. The conservation law is this, and this is added energy. This du is the change of the internal energy. The closed system works to rotate the impeller, and that's why the internal energy changes. Okay? And lastly, this PdV is the work done when the system changes its shape like this in a very short time. And now we obtain this equation. We got this equation by thinking about an open system, and we got this equation by thinking about a closed system. Both equations are true. Okay? And now I'm going to play with this equation. This is the definition of enthalpy. Let's calculate the total derivative of it. Next, let's expand this PdV, and it will be this, okay? I will continue calculating this. This was easy, right? And I will organize the screen. Next, I will substitute this into this equation to eliminate du, and then we can get this. Let's integrate both sides of this. Okay, and I will substitute this into this equation. This equation was derived by thinking about an open system. Do you remember it? And finally, we can get this equation. After reversing the bonds of this integral, we can get this. And this means this integral, right? Lastly, let's review this video. This integral means work done by an open system, the work that this impeller produces. On the other hand, this integral means work done by a closed system, the work that the molecules here produce when its shape changes.